All right, so differentiability. What does differentiability mean? It has a derivative, which means it has a slope at a point, the tangent slope. That's all, that is the same thing. So that point has to exist. So that's why I said the first thing we want to consider, right, is it continuous? If there's a discontinuity of any type, it doesn't matter if it's a removable discontinuity, a jump, infinite, it won't have a derivative at that point. So for example, here we have a piecewise function. I don't care that from the left the slope is 0 and from the right the slope is 0. That's kind of like what we had in that homework problem, number 42. You can't find the slope if the point is not connected from the left and the right. So, right, so there's a discontinuity here. If I can spell discontinuity at x equals 0. Now, you can find the derivative at any other point. You just can't find it at 0. Okay, so if I ask you to find the derivative at 3, that's fine. At 3, it's going to be 1.
Oh, so you can like break apart.
You can break apart a function.
And then it can be different.
Exactly. So if I said f prime of 3 at 3, oops, sorry, not 1. The slope is 0. Sorry, f prime of 0. I said the backwards. The value is 1, but the derivative, the slope is 0. But f prime of 0 does not exist. Okay, just we don't have it. Oh, that's right.
Oh, did you record? What is that? I don't understand.
So what's this? So the slope here is 0. The slope here is 0. However, right here, I can't find the slope because it's not continuous. Okay, so when we get to the examples, it'll make a little bit more sense because I'm going to go step by step. So step 1 is always look for continuity or discontinuities.
So would any number other than 0 would equal 0? So if you were to do like f prime of 2, would that also equal?
Yeah, that would be 0. So basically this has a derivative equal to 0 everywhere on its domain, except for at 0 it does not exist. Okay. All right, next one is a corner. So we've actually seen corners, but here's the actual definition. It's where the left and the right side derivatives differ. Okay, so for example, the derivative of 0 from the left. So again, here's my tangent line, right? My pencil, I'm holding it. So my tangent is that part of the line. Now what's the slope from the left? -1. And what's the slope from the right? +1. So since these are not equal to each other, we have a corner. Okay, and my corner is at x equals 0. So again, this one, I can find the derivative at 2. I can find the derivative at -3. I can find the derivative anywhere, just not at 0. So there's a corner.
Even if like this wasn't about the origin, like if it was just like
If it was moved over,
still there would still be a corner.
there's still a corner. Okay?
And so you can't say that at 0, like that doesn't exist.
F prime of 0 does not exist. These are just simple examples, but it doesn't have to be an absolute value equation necessarily. It could be any kind of piecewise function that we can look for might have a corner. And sometimes a piecewise function is continuous and differentiable at its entire domain. So that's why we have to check both sides to see what happens at that point. All right, next we have cusp. Okay. So this is kind of looks like the top, well, if you graph it, it almost looks like the top of a heart, right? It kind of has this square root look here, and then it's reflected. This is our example, x to the 2/3. So this happens when the slopes of the secant lines approach infinity from one side and negative infinity from the other. Here's what I mean. I say secants here. You can also consider the tangent. So what's happening from the left? So if I follow that, it's becoming a vertical line. So it's approaching a negative infinity slope here. And what's happening from the right side? It's approaching a positive infinity slope from the right. That's how we get that kind of shape at the top. Now,
How's that other one not also approaching negative?
Okay, don't think value, think slope. That's why I hold my pen here. What is my slope, positive or negative? Negative. Is it ever going to become positive? No. So it's approaching a negative infinity slope. Bless you. And then from this direction, do I have a positive or negative slope? Positive.
What's the difference between asking at the secant line? Like, what is that in comparison to tangent?
Secant is just using 2 points, tangent's 1. I'm using them kind of interchangeably here. Yeah, this is like taking 2 points, but we can think of it as one and the same for this example. Yeah, Maya?
I'm using infinity because it's like, because of the end behavior. I know it's not the end behavior, but because it's not approaching infinity.
No, we're not talking about the values, we're talking about the slope. Okay, when the derivative approaches positive or negative infinity, that's a vertical tangent. That looks like a vertical tangent from one side. Now that's different from the next one, but it's approaching like a vertical line. Just one's got a negative slope, one's got a positive slope. Now, this is exactly what we're looking for. We're looking for x to an even over odd, where the numerator is less than the denominator. So that could be 4/5. It could be, and also in reduced form, it could be, what? 10 over 15, okay? Which reduces, but what does that reduce to? 2 over 3. Okay. So anytime you have that even over odd, numerator is smaller than the denominator. So here we have, here I'll write it out with notation. Okay, so the derivative from the left, this is approaching a negative infinity slope, right? And then from the right, again, the derivative, the slopes, this is approaching positive infinity. So therefore, f prime of 0 does not exist. Yes?
I'm just a little confused why that one goes to infinity and the one above goes to negative 1. Or like 1.
Okay, slope, not value, slope. Do I have a positive, does my line have a positive or negative slope here as I trace it? That's negative, and it's getting,
But then what about the, I'm confused. Oh, because it stays straight. Okay, got it.
okay. Yes, Abby?
What if it's odd over even? Like, or something, or like the
Odd over even, x to the 1/2 is odd over even, right? X to the 1/2 is also known as square root of x. That is going to have a derivative everywhere except for the endpoint, but we'll get to that later. Don't worry about it. We're talking about on its entire, we're just talking about specifics right now. Vertical tangent. Now, this is whether they both approach positive infinity or they both approach negative infinity. So watch when I trace it. This is a cube root of x. So if I trace it, what happens? Do I have positive or negative slopes here? Positive. Does it say positive? Oh, then it becomes a vertical line, but then it still stays positive. You see the difference between that and the last one? Yeah. So this is where the slopes approach either infinity or negative infinity, but not both, okay? This is where you have odd over odd, where the numerator is also less than the denominator. So think of this can also be written as x to the 1/3, right? X to the 3/5 would be the same. X to the 1/9, right? So if you have something that's written in radical form, it's often best to just rewrite it as a rational exponent so that you can compare the numerator and denominator. Yes?
Can we know just by, like for the last two examples, just by looking at
Yep.
the function
Yep, that's what I want you to do. Yeah, that's what I want you to do. So the derivative from the left,
Good morning, D. Toledo. Today we have college counseling, college visits at Bonus and Lunch. The University of Connecticut is visiting at Bonus, and the University of California, San Diego is visiting at lunch. Please wish the girls' tennis team a good luck at their game today. We have a flag football game today as well, across the street. There's also a draw Zvar of the day going on today from 3:20 to 3:35 in room 185. Thank you all and have a great day.
okay.
I have another question. It's your dad. What do you mean?
Yes, Abby?
Why? Why is that like non-existent? Usually it's just like
It's got a vertical tangent. Okay. Is infinity, oh, I should have not written equals, but it's okay if you did. I'm just going to put a little arrow instead. They are the same, but is infinity a real number? No. So remember, it has to be a real number in order for it to be a derivative. So even though they're the same, infinity is not an actual slope. You know what I'm saying? So I can't, that's why we call it a vertical tangent. Yes, Molly?
for the corner.
Uh-huh.
How would it like? What is an equation that would like beat a corner that isn't an absolute value?
We will look at one
Because I don't really know that.
on the next example. Okay, Mayan?
If the tangent is vertical, is that why it's
Like yeah, things cut off.
Yeah. Okay. All right, example 1. So compare the right hand and left hand derivatives to show that the function is not differentiable. So I'm already telling you it's not differentiable at point P. Here's point P. So first thing I would check for is to make sure it's continuous at x equals 1. Well, if I plug in 1, I get 1. If I plug in 1 here, okay, so we're good. I gave you the instructions to check left and right hand, but I still encourage you to automatically make sure it's continuous at that point. Good? Okay. Left and right hand derivatives. Yeah, Ben.
It's not continuous, we just stop there.
You just stop there. That's why I always check for a discontinuity first. But this is nice and continuous. It definitely does not look like it's going to be differentiable at 1. Why? Because the slopes definitely are differing, okay? So what we want to do is left and right hand derivative. What's that mean?
With the H.
That's the H. Okay, so here we go. I'm going to find f prime of 1 from the left is going to be the limit as h approaches 0 from the left. Which function am I using? The x squared or the 1 over x? The x squared. Okay, so I'm going to have 1 plus x squared minus 1 squared. Oh, wait, you're right. I'm sorry. I didn't put the... Yeah. Yes. There we go. 1 plus h. Sorry. It's getting my x's and... There we go. 1 plus h squared. Okay, so that's going to be... What do we get? 1, right, plus 2h plus h squared minus 1 over h. We get 2. Yeah.
How did you reduce this equation?
Page 4.
We all have asked the same question so many times.
We're done with that question. Page 4. Page 4. You see page 4? How are one-sided derivatives defined with this equation?
Are you asking me?
No, I'm just restating.
Oh,
I'm just restating it. Just saying it over again.
saying what?
Okay, let's check from the right.
Oh, No, whenever it's going from the left
Whenever
to
it's
the
asking
right.
you from one side to the other, you always just go.
Page 4, page 4. Page 4, use page 4. Okay, from the right, now we're going to use that 1 over x. So that's going to be 1 over 1 plus h minus 1 over 1 all over h. Okay, how do we simplify? Common denominator, so we can multiply by 1 plus h. And then, what do we have? It's going to be 1 minus h over 1 plus h times 1 over h.
Oh, you don't need you just multiply it to the top, not like both.
Yeah, because it's just a 1.
Yeah.
Okay. And our 1s are going to cancel. H's are going to cancel, but I still have a negative 1 on top. So I get negative 1. Okay. So since the left-hand derivative and the right-hand derivative are not equal to each other, what happens at 1? But there's a corner. Okay, so therefore, there is a corner at x equals 1. There we go. Okay, so we showed that the two slopes, the slope from the right, and you can kind of see that, right? Geometrically, take your tangent line. That looks like a slope of 2. You want to also just confirm, according to the graph, does that look about right? From the left, yeah, that looks like a negative 1 slope. We can see right away when you have a positive and a negative slope, you're not going to have a derivative there, but this is how we would just verify it. Griffin, did you have a question?
Oh, yeah. I think it went away. Never mind.
It went away. Okay. How was that? Corner? Okay, Mayan?
So even, we just have to prove that it's a corner because, even though we can tell that it is.
Yeah, that's just verifying it. Yeah. Okay, you have pictures on yours. For some reason, sometimes when I save things as a PDF, you have pictures? You have pictures.
I got poverty one.
Oh, how come you don't have a picture? That's so weird. Ryan got, everybody else has pictures? I have no idea how that happened. Okay. Okay, anyway, basically, yeah. Yeah, anytime that the slopes from the left and the right are not equal to each other, it's a corner, as long as it's continuous. It's only when you get infinity for a slope or negative infinity, that's the cusp or the vertical tangent. Okay, generally speaking, with piecewise functions, we usually look for a corner. Now, could there be a vertical tangent and a corner within a piecewise function? That could occur, just it doesn't happen that often. Yeah, Griffin.
Well, for that one that you were just that one, how do you know if there isn't a removable discontinuity at the
Oh, that was what we checked for first. I didn't have that in the directions, but I just did that real quickly. I said, well, let's just make sure it's continuous. Plug in 1 here, plug in 1 here. We get the same value.
Well, so they have the same limit, but
Right, but they also equal the same. There's no removable discontinuity there.
okay.
Generally speaking, I'll give you the actual piecewise function so that there's no misunderstanding as to whether they're, you can actually check for continuity.
Okay.
Yeah, Molly.
Let's go back a little.
Oh, okay.
How come I'm a little confused for a vertical tangent. How come if they're both their slopes are both approaching infinity? Why? Is it just because infinity isn't a number?
Abby asked that. What do you remember what the answer was?
Because infinity is not. Well, that's
It's not a real number, so can it have a slope there? No.
okay.
Remember, it has to equal.
Same with the other one. The one on top? Or is that just because they're different?
They're different. They're different slopes. Let's do some more. We'll get there. We'll get there. Okay. Okay, differentiability. It's. I guarantee you, this is not the hardest thing you'll learn. Then you say, then it has a derivative. Then the derivative would be. Okay. On your paper, you have little graphs at the bottom. So basically, differentiability. Let me just explain what that means, local linearity. It just means if I were to zoom in to a graph, and it becomes a straight line. So see, I gave you a parabola, and I zoomed in and zoomed in and zoomed in. If I even zoomed in more, it'll look like a straight line. But what would happen if I zoomed in to this point? Will it ever look like a straight line? No. So then that's also another way to think of, is it differentiable? So if I were to zoom in on this part, then that would be okay. I'll eventually get a straight line. So that's why I want you to try to think of it as just keep zooming in, and will it have a defined slope? Not infinity slope, not negative infinity slope, but an actual number, and the same number from the left and the right. Yes, Maya.
Sorry, just because the example here would have been the horizontal line, which would still be 0, but if you zoomed in on a point and it had, let's say, a slope of 2, that would still be, like, differentiable.
2 from the left and the right, and it has a value?
Like, for this example, we zoomed in on the
Yeah.
and the slope was 0, but let's say we zoomed in on a different point and
Yeah, it should still be a straight line. It just won't maybe be horizontal. Maybe it'll be this way. Okay, let's do some calculator practice. We'll do derivatives. So this, you know, obviously there's no calculator and calculator portions, but if you're working on your homework and you want to check it, you have a number of different ways that you can do derivatives on your calculator. So I'm going to show you that.
The whole quiz is going to be like that. You just said there's going to be calculator and no calculator sections.
Calculator, okay. I'll give you a practice quiz at the end. Okay. All right, so I'm going to show you a couple ways. If you press menu.
Wait, you're not supposed to go with the graph part or the graph?
No, just in the calculator part. Okay, notice there is a calculator option, number 4. And you can find a numerical derivative at a point. Wait, bless you.
I think you meant calculus section.
You don't have a calculus section on the T?
No, you said calculator, but you meant calculus.
Calculus.
Oh.
Do you see it?
Now you're all caught up.
Okay, sorry, calculus, not calculator. We're all in the calculator section right now. Okay, and then
Go to menu, go to calculator.
it's number 6. Ari, yours is going to be, and
Go to regular, like,
Max.
like scratch pads. And then you go to calculus and click on the first
I know how to do this. I'm just drawing. There we go. Second trace.
Would you ever give us like a point like 1, like 2 or something, and then you would still plug in 1 for x?
It could be a different point.
Okay.
Yeah. Max, you're gonna do this. Calc. Yeah, perfect.
Did you actually expect to win?
Okay. dy dx. Okay, did we get that? Plug in 2. So what's going to happen so when you go through that, it's going to give you this d dx, and then that's where we want to type in x squared. And notice it gave, remember that little vertical line means evaluated at, so it's saying evaluated at x equals 2.
Oh, that's what that
Press, yeah, the vertical line means evaluated at.
Oh,
Okay, so, yeah,
you put the two.
x.
Oh, okay.
Okay, did everyone get that?
Oh, yeah, sorry. Oh, I get it.
You get it? Okay. There's also a shortcut to get to the derivative. Right next to you have like a little catalog button. That's where you can search for stuff. To the left of that, you see that button that I selected? And there is a shortcut on the TI-84s. I'm trying to remember. I think it's something 8, but you see it?
Oh, I see.
And then do you see how it pops up all these different options?
Yeah.
So you can also select, right? Oops, that's the second derivative. Sorry. It was really small. I couldn't see it. Okay. So that's another way to get there.
Oh, okay.
It's always going to be d over dx.
It's always going to be d over dx.
So here you want to put in your x manually?
That's the second derivative. We'll talk. Don't worry about that yet. It doesn't give you the option. Can you put?
Like ends up like this, and I plugged it in, and then there's no.
And then you do x squared and then x equals 2.
Oh, maybe.
It's a coincidence.
Okay, maybe we'll.
Wait, how do you do it on?
Okay, let's do the graph. Oh, I can't. Hold on. I wanted to show you through the graph, and then I'll address questions. I don't want to waste too much time on the calculator part.
No.
Okay, if you go to the graph, and let's say we want to. Now we're in the graph part. Okay, graph it. All the steps are here, guys. All the steps are here. Okay, so this is if you want to look at it on a graph. So number 6, when you press menu, there's an analyzed graph, number 6. And number 5 says dy dx.
Oh. Wow, and you can just go to a point?
Uh-huh, and you could just
Type in like 2.
2. And look what it does. Just type in 2, and it will give 4. TI-84s are a little different. You have to go to, do you see it on the menu?
Mine's even doesn't.
Oh! This is crazy. This case.
Every time I press the, like I found
Wait, where do you
like number 6 is, but every time I press on 6, it automatically takes me to a graph.
Type in 2, and then press enter.
Oh, because yours just takes you straight to what our graph does. That makes sense. You just have to plug in the unit. Oh, okay, so it won't show it to me like as the equation.
Right? Okay, did we all get 4?
Yeah.
Yes.
Even like this
Oh, you gotta press that button.
You have to press enter after you've typed the number. You could do it. You just go to the 6, and then you have to type in 2, and then press enter.
If I don't have a graph,
Oh, you have to put a graph in. So do,
then when it's
I'll press the 2.
but type in x squared.
I'll press the 2.
Yeah, squared. Okay, press enter. Graph.
yes.
And then second calc. dy dx. And then type 2, enter. There you go.
Yeah, or when you do it,
Yeah.
that one's
Okay, that you have to go to second.
So we finished the curriculum.
Let me help you at the end. Okay. All right, we still have a lot to do, so let's, if we're having calculator issues, save for later. Okay, that's not a big concern right now. Okay, differentiability implies continuity. That means if it's differentiable, so if I tell you there's a differentiable function, then you know it's continuous, so you don't have to check for continuity. All right, so just quick note, the converse is not true. So, right, we talked about, right, the converse. Remember converse? Where you switch the hypothesis and conclusion of a conditional statement. Don't ask what math that's from, Scotty. Okay, well, don't tell your teacher that. Okay. All right. If it's continuous, that doesn't mean it's differentiable. Remember, we talked about those exceptions, the corner, cusp, or vertical tangent. Okay.
It's continuous.
If it's
continuous, it's not necessarily
correct. So if it's differentiable,
in rectangles.
it's just the reason I want you to know that is there are times where I need you to justify why you can apply certain theorems or this or that. So if it's differentiable, we automatically know it's a nice, smooth, continuous curve. Okay, but that doesn't mean, right, it could still have a cusp or a vertical tangent. Well, I shouldn't say smooth, but you know what I'm saying? So if it's continuous, it doesn't mean it's differentiable, but if it's differentiable, it's continuous. Okay, let's take a look. Here we have a graph over a closed interval. We don't know the equations, but we just have the values here. So at what domain points does the function appear to be differentiable? Okay, so let's look for part A, differentiable. So let's go from the left to the right. It looks like we can include -2 until we get to -1, because it looks like there's a corner there, right? So here's what I'm going to do. I'm going to put -1. I'm going to use a parentheses for these. Okay, then we go from -1 to 0. We're not going to include 0 though, are we?
No.
No, because there's a discontinuity. We don't care what kind of discontinuity. It happens to be jump, but it doesn't matter. And then what? Okay. Actually, let me. 0 to 2.
What if the 0 is... Oh, yeah.
It's a discontinuity at 0.
Oh, because it's...
We only include the endpoints, the final points. And then 2 to 3, I'll close the brackets for 3. So I'm not including 2 because it's a removable discontinuity. It's still, we can't have a derivative there. So all of these pieces, so we could see 1, 2, 3, 4. There should be 4 parts to our interval that are continuous. Yeah, Ben.
Why is it not continuous at -1?
Okay, we're not asking continuous. We're asking for differentiable. Next we'll do continuous. What's the difference between what? What does differentiable mean? Has the same slope from the left and the right, and it has a value there, right? But you see how this is definitely a corner. It's got a negative slope here and a positive slope here. Okay. All right. Now, continuous but not differentiable. Well, we were just talking about that. Where is it continuous but not differentiable? In other words, B is asking, where do we have a corner or a cusp or a vertical tangent? That's what B is asking for. Correct. So I don't have any cusps or vertical tangents here, but I do have a corner. Where does that occur? At -1. Okay. And the last part, neither continuous nor differentiable. So it's going to be at the discontinuities, exactly. Okay, and that will be at x equals 0 and 2. So it's a lot about the vocabulary here. It's more vocabulary than it is actual math, right? You have to understand when I say differentiable, what's that mean? If I say continuous but not differentiable, now we're looking for those specific corner cusp or vertical tangent. Okay, I know it's a lot to put together, but practice, we'll be fine.
So when you say at x equals 2, is that like referring to going stop at it?
I'm looking for discontinuities for part C. That's what I'm looking for. Okay, the function fails to be differentiable at x equals 0. Determine whether the problem is a corner, a cusp, a vertical tangent, or a discontinuity. All right, so 4/5, even over odd, cusp. Even over odd. So this is going to be a cusp. I don't actually have to show any work for this. If you have your calculator, you can probably graph it as well. What about 1 over x? There's a discontinuity. Right, we know that they're, right? If we were to look at this, this is the graph. Yeah, that's a discontinuity. I can't spell discontinuity today. Just ignore the way I spelled it. Okay. You just need to know what the graphs look like. Okay. Find all the values for which the function is differentiable. Okay. I know.
Should we like?
Let's factor it.
Let's factor it.
Go ahead and factor it.
Go ahead.
Do you remember the difference of cubes?
Yeah, we do like the x
We
squared.
do the triangle.
Oh, is that the pyramid?
That's working backwards from the triangle thing.
Is that Pascal's triangle?
Oh, yeah. No.
So it's like the, I think.
I don't remember.
I don't know how to. I don't know how to calculate
Oh, she really did.
Wait, how does that work?
She's gonna be mad if we don't know how to do this.
I can hear you. Another, if you forget the formula, you should know, like if it's x cubed minus 1, then x minus 1 goes into it. Do you remember that?
Yeah.
Like if it was x cubed plus 1, then x plus 1. And could you do a quick synthetic division or something to find the resulting quadratic? Okay. All right. The first thing I want you to consider is domain. Okay? I want you to consider the domain because, so consider domain first. Really, what do we have here? We have a removable discontinuity at 1 and an infinite discontinuity at -1. I don't care what kind they are, I just care there's discontinuities. So it's going to be differentiable everywhere else. Now, the numerator, did I really need to factor that out? No. If I was asking for what types, then I would need to factor it and recognize that there was a removable discontinuity. But all I care about is where is it going to be differentiable? So it's going to be from -infinity to -1, -1 to 1, and 1 to infinity. And that's it. I just need to consider, because this is a rational function, there's no corners, cusps, there's no vertical tangents, okay? There's no corners. It just has discontinuities. Okay, so that's why all I care about on that first one is domain. Okay, B, this has all reals for the domain. Okay, so there's no discontinuity. So now I go next. What are my other problems? A corner. Does this have a corner? Doesn't have a corner. Remember what this would look like? This would be like over 2, up 1, 2, 3. I think I heard Molly say it. A tangent, a vertical tangent. So where does that vertical tangent occur? Do you see how this is really x minus 2 to the 1/3 power? It's odd over odd. Where does that vertical tangent occur? Where does it occur? At x equals 2. So it's going to be differentiable everywhere except for 2. You see where we're going with this? So we're checking domain first, then we're looking for one of those corner cusp or vertical tangent. And if that occurs at a location on the domain, we're going to exclude it from our intervals for differentiability. Okay. That sounded more complicated than it actually is, but
Do you mind repeating what you just said?
what did I just say? First thing we check for is continuity. If it's continuous, then we look for a corner cusp or a vertical tangent at some point on its domain. And if that occurs, we're going to exclude that from our intervals of differentiability.
Okay.
I recorded it, so you can rewind it and go back.
Why not or was it like
That's where the vertical tangent occurs. You see how it's a. Do you see how there's a translation here? We moved it to the right too. The +3 has no relevance on where that occurs. It's just the x. So basically what you want to do is just look at the horizontal shift is going to be where that vertical tangent or whatever is occurring. Okay, next one we have is a piecewise function. Let's check for continuity first. We plug into here. 4. Plug into here. So there's a discontinuity at 2. So I get to include everything but 2. Okay. What about the last one here? We also have a problem. It's also not continuous. So everything but 1. Oops, why did I write? Jumping ahead to the next part. Good time. Okay. Good. Now, what would happen if it was continuous? Then what would I need to do? I would have to do the limit from the left and the right and see if those match. If they don't match, then that would be a corner. If they do match, then where would it be differentiable? All reals. Bless you. Okay, I think this is the last thing. Oh no, there's 2 more things. It's okay, it's easy. Okay, real quickly, we actually had this, I think, in the summer packet, intermediate value theorem. Or is it in the first chapter? Okay, I was trying to remember because it's usually a review from pre-calc, but you don't really do much application to it until you get to calculus. So intermediate value theorem just basically says if I have a point down here and a point up here and it's continuous, it has to take on all those values in between. It could go past them, but it has to have y values in between. So, for example, if I have f of 0 equals 2, so I have a point here, and f of 2 equals -3. Bless you. So that means, right, if I have 2 and -3, there must be a point C in that interval such that f of c equals 0. So there has to be a point where it crosses the x-axis. What other possible values could f of c equal? What could f of c equal? 1. F of c could be equal to 1.3. Okay, right? So anything in between there. Again, you'll see more applications to that when we actually get to the FRQs for the test. So, okay. Good, yeah.
So F of C can equal anything up to 2?
Anything up to 2. And anything down to -3. Could f of c equal -5? I mean, Could, but we don't know for sure, so we wouldn't include it in the values, right?
These are y values, right?
These are y values, yes. So intermediate value theorem is specifically referring to the y values on a closed interval. So they're saying from here to here, right? I'm just restricting it from. I could go down to -3, but I'm restricting it there.
Our y values between 2 and negative
2 and -3. So it has to be between 2 and -3.
Right. You were at 3 because they're y values.
Oh, I was saying X, right?
Oh, you were thinking x values.
Yeah, that's what I said.
That's why I was like,
Oh, it could be -2.
Oh.
It could be -2.9. I'm referring to y values, not the x values. But that's okay. Those x values worked also.
yeah.
Okay.
Why couldn't you do -4 for y value?
It's not bad.
Because it has to stay between 2 and -3. I know, but Abby, we don't always have a picture to go along with it. Okay?
X values have to stay between 1 and 2.
What's it called? I made like 5 of them.
Okay.
Why did the x values stay between 1 and 2?
Because, or between 0 and 2, that is. Yeah. That was the domain. Okay, last thing here, guys. And I know it's been a long class here. Intermediate value theorem for derivatives. Okay.
Oh, it's a different one.
It's a different one. This is specifically for derivatives, but it's the same idea, right? So we have to first have a differentiable function. So that means it has to also be continuous. The previous one, I didn't highlight it here. All we needed on the intermediate value theorem was a continuous function. We didn't care that it was differentiable. But because this one is for derivatives, we need to make sure it's differentiable. Okay, so it basically means f prime is the slope, right? The derivatives, they take on every value between f prime of a and f prime of b. Okay, so let's look at a practical application. So let's say here we have f prime of 1 is -2. We're talking about slope now, not values. So kind of picture here's -1. Oh, that's not a good tangent. Hold on.
Isn't it positive 1?
Oh, thank you. I totally missed that. There. There we go. There's my slope is -2. And at f of 2, right here, now my slope is -6. So that means my tangent slopes have to stay between -2 and -6 for sure. Could it go beyond those? It could, but I can't guarantee it, right? So if I picture, here's my line, right? There must be a point C such that f prime of C could be equal to what? Just a random. -4. Okay. What other values could f prime of C equal? Now you see, this is referring to slopes. -3. It could be -5. -5.9. So that's how the intermediate value theorem for derivatives. It's, again, I think I used this analogy before, right? You're driving, let's say you start, it's kind of like average value in a sense. Let's say you start from home, right? You're starting at 0 miles per hour, right? And your highest speed is 50 miles per hour. So at some point on your speedometer, it has to read 30 miles per hour, right? You can't skip over numbers, right? You start 0 miles per hour, your highest one is 50. That means you have to, at some point it's going to say 10 miles per hour. At some point it's going to say 30 miles per hour. Okay, so that was it. Let's last minute questions. Abby? Shh. Oh, that's just on a specific domain. Okay.
Yeah, I'm confused on.
Casey, are you available at lunch to meet? I'm so genuinely confused.
Yeah.
I am just I'm just using 1 and 2 because those are the values I gave you. So I'm specifically, now I could have said from -4 to 0, and it still applies. So if I had said at -4, here's my slope is, I don't know, -2, let's say, and at 0, my slope is 0. So so that means I might have different slopes, but I have to have values that are between -2 and 0. So it just depends on what, I have to have it on a closed interval. Like I have to, because I'm talking about specific values. Does that make sense? It's just, this is the domain, this is referring to the slopes. Okay. Other questions? Let me get you the practice quiz. Now, tomorrow, when do we have?
After lunch.
After lunch. So, let me try to think, because I know some of you have extended time. Yeah. Yes. The quiz will be. It's not very long. I can't. It might. Also, I just have to tell you, I didn't leave a lot of space for things, so it will be stretched out over more. Sometimes I try to save paper for practice quizzes and tests.
That's fair.
But on the actual quiz and test, I give you more space.
When's the actual test?
On the quiz.
It's not.
What'd you ask?
It's on my job.
It's on my job. I don't know if I have any extras.
Oh, it doesn't say the date on this one. You can change it.
Okay.
Okay, it's the 13th.
We have, why don't we look over since we have a few minutes left, take a look at the practice quiz. So notice the first two, yes, so not always will this be the case that it's calculator okay. This quiz will be all calculator okay. The first two, notice what I gave you. I gave you the formula because I want you to practice this one because we've done the H approaches 0 a bunch of times now. Now I want you to use this new formula. Okay? What's that?
Are you gonna tell us on the quiz?
Yeah, yes. I'll say the formula.
Casey, you're so clutch.
I'll give you the formula, okay? So notice the numbers 1 and 2. I want the formula, so you should have X or A in your
At the end,
answer.
you just plug in A as like the variable.
Yeah, if you write it in terms of X, that's okay. I'm not real picky about that.
Wait, what is
Yeah, because it ends up being A.
Right, so, and I believe I already posted, did I post this already? I want to say I did. Right, so